I'm Jess Scott, and I'm going to share with you some findings of my thesis. Estrogen and other hormones in the environment have been linked to physiological and reproductive impairment of birds, aquatic species, and wildlife. Researchers have linked exposure to decreased sperm counts and malformations of the male genital tract and to certain types of cancer and endocrine-related diseases. Human health risks associated with environmental exposures are still largely unknown and controversial. Livestock waste from large confined animal feeding operations, or CAFOs, are estimated to contribute over 90% of the environmental estrogen load. The land application of waste as fertilizer creates a widespread non-point source situation for the hormones livestock waste contain. Livestock waste contain hormones naturally excreted by their bodies, as well as pharmaceutical hormones livestock are administered to enhance growth or meat quality. The amount of hormones livestock excrete depends upon species, age, size, sex, gestational stage, or castration. But the amounts and types of hormones excreted are not the same that are found in runoff from fields. Hormones break down through collection, storage, and treatment, and after land application. Rates of transformation can vary drastically, dependent on situation or environmental context. This makes it impossible to calculate rates of transformation or degradation across complex environmental gradients or through landscapes. Researchers find that hormones in land-applied waste like to absorb to soils, and that the strength of absorption depends on the soil type and texture. Hormones have a high affinity for soil organic carbon, so they will bind up best in soils with high organic carbon contents. The transformation and degradation of hormones in soils is primarily mediated by bacteria, fungi, and algae. Fields act as a sink for hormones. Hormones bind to soil after waste are land applied, but are quickly released in saturated situations after storms or during snow melt. This creates a flush of hormones, as illustrated in the spike in the graph above. Across a landscape, hormones move with the flow of water. They have been measured in runoff from fields, in drain tile and ditches, and in down gradient streams. Hormones also leach to groundwater, where they can move to surface waters. Knowing these characteristics, I thought, which streams in Missouri are most likely to be affected by hormones from land-applied CAFO wastes? Hormones change and break down at a multiplicity of fine scales, but they move through the environment at broad scales, landscape scales. This suggests that we cannot predict exactly how much of what kinds of hormones will get into downstream surface waters. But if they were getting into surface waters, I wanted to predict where they would be found. First, I needed to figure out where these land application fields are. Waste application follows prescriptive, field-specific nutrient management plans. The locations of land application fields, which can change from year to year, are described in these plans, but this information is generally kept on site. I don't have access to that information, so I don't know exactly where wastes are spread. This is a land cover map of the whole state. Wastes are applied to croplands and pasture lands. So this map gives you an idea of how much of Missouri is agricultural land that fits that type. You will see in the next slide that when CAFOs are spatially concentrated, access to land application fields may be confined. I used a publicly available data set of permitted features at CAFOs as a proxy for the locations of the CAFOs themselves. There are 573 permitted CAFOs in Missouri, 296 hog operations in pink, 257 poultry and egg operations in yellow, 6 beef feedlots, 12 dairies, and 2 general farms. From my research, I found that wastes are expensive to haul, so facilities will spread them on lands they own, rent, or lease as close to CAFO facilities as possible. USDA Ag Research Service states that CAFOs usually apply waste within 16 kilometers of facilities. But if you make a buffer 16 kilometers around a facility, that contains almost 200,000 acres. That seemed like a lot of land. So how much were CAFOs really going to need? I went to the DNR website and reviewed some permits online, and it turns out that some facilities only need 200 or 400 acres to dispose of waste, but some facilities need 10,000 acres or more. It all depends on the number of animals they have, the volume of waste they create, and the fertilization needs of the land application fields they have access to. I started with USDA's suggestion of 16 kilometers and then created 2 smaller buffers. Based on the economics of waste hauling and the amount of cropland and pasture lands available, facilities are most likely to start spreading close. Therefore, I hypothesize that streams within smaller buffers are more likely to be impacted than streams further out. So I started with a 4-kilometer buffer. I modeled the runoff from each buffer, which includes all the runoff from land application fields within that buffer, which is the circle you see. Runoff patterns are the aqua lines. I layered those runoff patterns with stream network data, which are the dark blue lines, to locate streams most likely to be affected by that runoff. Headwater streams appear to be most likely impacted. Impacts are extensive in areas where CAFOs are concentrated. Very few watersheds are not impacted. Although a CAFO facility may be located in one watershed, land application fields often cross watershed divides. A study published earlier this year found significant positive relationships between the density of CAFOs and hormonal activity in streams in the Shenandoah River Valley in Virginia. If we correlate that study to the results of the model used in this study, it can be expected that increased hormonal activity will be found in watersheds in the southwest, north, and central parts of Missouri. Although my model was simplistic, it's informative to environmental monitoring efforts. Fine-scale studies have told us what to sample and measure, while broad-scale studies help to tell us where to look for the things we cannot see. Some good news: complex aquatic ecosystems like wetlands have been documented as having the ability to remove hormones, pesticides, and other toxins from water and wastewaters. Constructed wetland systems, as part of a CAFO's waste collection, storage, and treatment system, have been found to remove over 90% of hormones from livestock wastewaters. Tillage methods and vegetative filter strips may also reduce the concentration of hormones in runoff. Livestock makes a damn fine fertilizer, but land application fields are a large and significant potential source for environmental hormones. It is the concentration of animals and waste and the concentration of facilities that constrains effective waste management and effective environmental protection.